Pani, you can start now. Pani.
Yes, ma'am. Yes, ma'am. Yeah, ma'am, can you hear me? Hello?
Start, Pani.
Okay, ma'am.
Yes, Pani.
Good afternoon, everyone. Welcome to 105th episode of Creative Weekend Online Talks. I am Panindra, a creative volunteer. Thank you for joining us today for this exciting talk on temperature and thermophysics of the moon. Today's speaker is Dr. K Durga Prasad. I welcome you, sir, for this talk, and I thank you for sharing your knowledge and research with us today. Now, I will be your host for today. Creative is a group of people who are like-minded and curious to gain knowledge. The vision of Creative is to build constructive thinking on various domains. Every Saturday, we organize online weekend talks on Zoom platform and we live stream it on our YouTube channel as well.
Pani, you are muted. Maybe. Pani, his audio, maybe some problem, sir.
Yes, I'm back. Something interrupted. Someone remove me from the meeting. Okay, sorry guys. Let me start the hosting. Every Saturday, we organize online talks on the Zoom platform and we live stream our program, our YouTube channel as well. Creative is thankful to all its resource persons for engaging us with their knowledge. I am delighted to stand before you today to delve into the fascinating realm of celestial exploration, the temperature and thermophysics of the moon. Our closest cosmic neighbor has long captivated our imagination and has been the subject of numerous scientific investigations. Beyond its mesmerizing beauty, the moon holds crucial insights into the dynamics of planetary bodies and intricate dance between light and heat. In this talk, we will embark on a journey to uncover the mysteries of lunar thermophysics, where we will explore the intricate interplay of temperature, radiation, and the unique lunar environment. Our understanding of temperature on the moon is not only vital for comprehending the past and present conditions of the celestial body, but also holds implications for future lunar exploration and potential habitation. Our exploration of the moon's temperature and thermophysics is not merely a scientific pursuit. It is a journey to the heart of a world that has been stirred our imagination for millennia. But comprehending the intricacies of the moon's thermal behavior, we unlock doors to the knowledge that may impact not only our understanding of lunar process, but also our aspirations for humanity's future in space. So I invite you to join me as we unravel the enigmatic relationship between temperature and moon's captivating landscapes, navigating the realms of thermophysics and embarking on a quest to illuminate the moonlight mysteries and that have fascinated humanity for generations. But before that, let us not forget that birth anniversary of Dr. Vikram Sarabhai, a visionary who ignited the flames of scientific curiosity and national pride, a true pioneer, the driving force behind India's space program. Dr. Sarabhai's legacy continues to inspire generations as we stand on the threshold of new cosmic frontier. Let me now invite Shivas, a creative participant, to give a glimpse about Dr. Vikram Sarabhai and his legacy.
Can I start?
Shivas.
Yes, yes.
Good afternoon, each and everyone. First of all, happy birth anniversary to Vikram Sarabhai. I am Shivas of class 6. I am going to express my views of Vikram Sarabhai. Vikram Sarabhai is known as the father of Indian space program. He was also well known and famous scientist, physicist, and astronomer. Vikram initiated space research and helped develop nuclear power. He belonged to a family of industrialists. Mathematics and physics were his favorite subjects. Apart from this, Sarabhai also had an interest in industries and business and development issues. In 1966, he got the Padma Bhushan Award. His full name was Vikram Ambalal Sarabhai. He did a research on cosmic rays under the guidance of Professor C.V. Raman at the Indian Institute of Science, Bangalore. He was born on 12th August 1919 in Ahmedabad. He was from a famous Sarabhai family. His father's name was Ambalal Sarabhai, who was a Gujarati industrialist. Married a classical dancer, Mrinalini. He went to England and got a PhD degree from the Cambridge University. He was a great institution builder and helped in establishing a large number of institutions. He established the Physical Research Laboratory in Ahmedabad. Kodaikanal Trivandrum. He also established a TIRA community. Science Center and Space Applications Center. He set up a rocket launching center at Thumba and later a rocket launching range at Sriharikota. Vikram Sarabhai was given a Dr. Shanti Swarup Bhatnagar Memorial Award. For his contribution to space technology, he was appointed as the chairman of the Atomic Energy Commission of India after the death of Homi Bhabha. He also helped in developing indigenous nuclear technology. Vikram Sarabhai died on 30 December 1971 at the age of 52 due to cardiac arrest in Thiruvananthapuram. Before that, he talked with APJ Abdul Kalam for an hour on the telephone. His body was cremated in Ahmedabad. If we don't have Vikram Sarabhai, today is not possible to launch many satellites, examples Chandrayaan-3 and Chandrayaan-2, etc. Due to this effort and contribution in science and technology, today India got a place in national level achievements. Otherwise, India became backward and lost its achievements national levels. Really, we are all proud to get a scientist like Vikram Sarabhai. Due to the achievements and contribution of Vikram Sarabhai and other scientists, today Chandrayaan-3 put a step on moon. Its all dedication goes to Vikram Sarabhai, who organized ISRO. Thank you.
Thank you, Shivas. Thank you, Shivas. Moving on to our today's talk, Ms. Uma will introduce today's speaker to us.
Thank you, Panindra. A very good afternoon to everyone present here with warm greetings. It is indeed a great pleasure to extend a warm welcome on behalf of Reactive team conducting a wonderful webinar on temperatures and thermophysics of a moon by a resource person, a man with a great vision and mission, Dr. K Durga Prasad sir. He pursued a profession of faculty at Planetary Sciences Division of PRL. He has pursued his MSc from Andhra University, Visakhapatnam, MPhil from JNTU, Hyderabad, and PhD in Planetary Sciences from Physical Research Laboratory, Ahmedabad. He has ample research experience in the fields of space science and planetary science and exploration with 15 years of experience at the Physical Research Laboratory, Ahmedabad. With a great geniality, his research includes laboratory experiments under simulated planetary environments, numerical modeling, and satellite payload development. He is the PRL principal investigator for Chaste, a payload of Chandrayaan-2 and Chandrayaan-3 landers. As a PI, he is also leading 3 other payloads to be flown on future missions to Moon, Mars, and Venus. He has recently developed a three-dimensional thermodynamic model of the moon, which is the first of its kind in the world. This work has been well acclaimed and reported as a research highlight of ISRO in Nature India and widely reported in print and online media. The idea of wireless sensor network for moon proposed by him has been highlighted on the front page of Times of India and renowned Nature India magazine. Our ecstatic and enthusiastic guest has been awarded with LPI Career Development Award in 2016 by Lunar and Planetary Institute and many more. He has published nearly 40 research papers and 2 popular articles in journals. He has delivered more than 25 invited talks in various forums related to space and planetary science. Cheers to you, sir, and once again welcome you, sir. Once again, I welcome you all. Thank you.
Thank you, Ms. Moon. Now over to you, sir. You can start your talk. Sir, am I audible?
Durga Prasad sir, are you able to?
Durga Prasad, sir, can you hear us?
1 minute. He is in the meeting. Just give him some time.
Okay, ma'am.
And 2 minutes. Network issue maybe.
Okay.
He is joining. His network is not connecting. 1 minute. Srinath sir,
Yes, madam.
some network
hear?
issue. He will join, sir.
Okay, good. Meanwhile, before he joins, just for the audience benefit, you might have read in newspaper or TV that 10th early in the morning, there was another launch by the Russians called as Luna 25, which is exactly similar to what Chandrayaan 3 you people are hearing from ISRO. So it is launched. It is today. It is moving already towards. Generally, remember from Moon to Earth, roughly 4 lakh kilometer or 3,69,000 to 3,85,000, like approximately 4 lakh kilometer. It takes around 5 days to travel. So Russians have launched a program called Luna 25. We have already reached Moon. We are in the orbit, which you have already seen in newspaper elsewhere. They will be reaching after 3 days or 3.5 days from now, and they will take some more time. One orbit they will revolve around it. Probably the Russian space agency news says they will be landing on either 21st or 22nd. India is landing on 23rd. So,
Durga Prasad sir, back sir.
Okay, good. I will finish last statement.
Okay.
Most probably on the South Pole, both of us are landing. That will be an interesting event on 22nd or 23rd, both this depending upon the convenience. You can have a look at it. Thank you. Over to Durga Prasad.
Hello, Durga Prasad, sir.
Sir, we are not hearing you. No, sir. We are able to see you, but not the audio.
Is my voice audible?
Yes, sir, but sir voice is not.
Okay. Till he comes back. As of now, around the moon, there are so many spacecrafts which are revolving around. Of course, you are aware, Chandrayaan 3, Luna 25 is going to come. Chandrayaan 2 is there. Even Chandrayaan 1 still in the orbit. It may not be functional, not active. There is Artemis spacecrafts are there, Themis B, Themis A. Then Korean satellite is there, which is also revolving around the moon. So like that, currently moon is very active. In future, there are some 5 to 10 missions are lined up. Next year, next to next year, Artemis has a big program. So in this decade of whatever you saw, 2023 to 2030, moon is going to be very active for the researchers to study on the moon. So more number of missions will be there. Probably moon may become launch pad to go further into the planetary, what you called Mars and beyond. So that's the kind of importance which has been there for moon since Chandrayaan 1 days, if you want to say. From 2008 onwards, the interest to the moon by the global research has increased. That is the kind of impact which India also has made because of its Chandrayaan 1 mission, which has resulted in the discovery of water molecules or OH minus and H2O plus type of molecules. And later, many missions by NASA, which is called LRO, LCRAS, these missions have discovered the presence of more water in the form of ice in the South Pole. So South Pole is probably having more ice. That's the reason these two missions, Chandrayaan 3, Luna 25, are focusing on South Pole. If you ask South Pole, which is looking towards Earth, already people may be aware that moon is tidally locked. Only one face of the moon is visible at any point of time on Earth. That is called the tidally locked face. And the that we say front face are looking at us. Other one is called rear or a backside. That particular region, China has also landed in the South Pole. So the first country to land on the other side of the moon, that too in the South Pole, is China. China's missions are called Chang'e series, CHANGE, Chang'e, 1, 2, 3, 4, 5. Like that, they have a many sample return missions, as well as they are. See, generally, what happens on moon, 1 day is equal to 14 Earth day, whether it is a light day or night day. So that many days only we can work. But Chang'e works even after one moon day. We say with 14 Earth days. After that, darkness will come, Amavasya type. Darkness will come. After 14 days, again sunlight comes there. It still works. Luna also has similar thing. So there are more revised or revived interest towards the moon, understanding of the moon. If you look at the moon, if you want to understand the moon, kindly use a computer application called Virtual Moon. It is freely downloadable in your desktop. Then you can play with the virtual moon to know the different craters, North Pole, South Pole, high resolution pictures, previous Apollo landed missions, all those things, images are available. People can play with that. And for the what you call the scientific credit, there are many creators' names in the name of scientists, great people. In that sense, Sarabhai name is there on the moon surface. C.V. Raman name is there. Homi Jahangir Bhabha name is there. Kalpana Chawla, astronaut, her name is there. And Mitra, one Bengali professor name is there. Like that, 5 to 6 Indian names are honored by naming few craters on the moon surface. Likewise, many world famous personalities, scientist names are there. It will be one interesting exercise. Go to the Google Moon. You can see the planetary bodies. Try to see the names of craters or names of region and various things like that. So you can study on the surface just for the nomenclature only, how they have named, what is their contribution. So on moon surface, there are 5 Indian names are there. By any chance, if somebody says site is there in my name, Shah Rukh Khan name is there, some hero name is there, please don't yield to such kind of news or information. You can fact check with Lunar Planetary Institute website or Virtual Moon. There are some authentic websites where these things will be there. Please fact check it. Then you can have a scientific study of the moon morphology, measure the diameter of the crater, how dark it is. Same crater, if you go to LRO website, which is called South Pole Atkin crater, on video will be there, where it will be showing you the variation of darkness, what you call shadow and lighting area on a crater rim. You can really understand how a day changes there or lighting condition changes there. There are certain interesting regions on the moon surface called EPL, Eternal Peak of Light. So it never becomes a shadow in the southern pole, especially. It will be something of order of Himalaya type of height craters or mountains. On the mountains, always sunlight will be falling. Researchers and scientific investigators are interested in such kind of places where they want to install permanent solar production, solar plants to generate a power. And there are certain places which are called permanent shadow.
Am I audible now?
Yes, sir.
Yes.
Yes, sir. Go
Yes.
ahead, sir.
Over to
Srinath,
Durga.
sir. Yes,
Over
sir.
to
Yes, sir.
Durga.
Actually,
Yes, sir.
okay. But some echo is coming.
You can share your screen. Sir, you mute in laptop, sir. You mute your audio. Now you can talk in your mobile, sir. Again, you muted, sir. So check your audio.
Yeah. But
Yeah. Sir, there is one option, more option. Sorry, mute.
So just unmute your phone's audio.
He's not connecting his audio through laptop. That's the
Yeah.
problem.
Yes, ma'am.
is it okay now? Can you
Yes,
hear
sir.
me?
Yes, sir. Yes, sir. Yes, sir.
I think now it is fixed. But
Yes, sir. You go ahead, sir.
whether you are hearing from my phone or laptop, I don't know. But anyway, now I think we can go ahead.
Yes, sir.
Yeah, thank you very much. And I'm extremely sorry for, I don't know what the technical problem is. It was working fine before when we tested. But anyway, now it got fixed. Hopefully we don't have any other problem now. And thank you, Srinathji, for your nice background and all information, which would be useful and filling up the gap. So, okay. So shall I go ahead?
Yes, sir. Please.
Okay. Yeah, thank you very much, Creative, for giving me this opportunity. I'll just first start sharing my presentation and then I'll speak. So is my slide visible? Is my
No,
slide
sir.
visible?
No, sir.
Okay, I think I have to share my screen. Okay.
Yeah, yes, sir.
Okay, it is visible now, right?
Yes, sir. We are able to see. Yes, sir.
Okay. Yeah. So a very good afternoon, all of you, and thank you, Preactive. So before I start talking about the temperatures and thermophysics of the moon, I would like to first pay tributes to the father of Indian space program, Dr. Vikram Sarabhai. Today is his birth anniversary. Because without him, I think he is the person, father of space program, has started space program in India. And I would say that today, if I'm talking to you on this platform, so basically it is, he has laid the foundation for space program in India, and several people got opportunity like I'm also working. So I'm very grateful, thankful, and great namaskars to the legend of India, Vikram Sarabhai ji, before going to the talk on his birthday. Yeah. So now I'll go to the topic. My topic is simple yet complex, which is temperatures and thermophysics of the moon. So as you see, this is some cartoon which I tried to put everything. Just have a glance at it. I'll not tell what it is. What does it mean? By end of the talk, I guess you will be able to realize what it is. You see some colored things here. You see some drilling over here. You see some subsurface. You see something going on away from the moon. And then you see some activity. Okay. So I'll not tell the importance, but later I'll try to emphasize upon. By the end of this talk, I think you will understand about it. To begin, our moon. So our moon is the nearest neighbor, and it is the fascinating object in the night sky. So if you happen to go out, particularly on full moon days or the days before or after the full moon, you would be very excited to see the moon. Everyone, I don't think that anybody would be there who will not look at. So they will be gazing at the moon because that is a fascinating object. Not because just because of its beauty or its night light, but because of several things. So as a scientist, if you ask me, why moon? What is so particular about moon? Moon has embedded in itself the secrets of our universe, the formation and evolution of our Earth and the terrestrial planets as a whole. So scientific understanding of the moon will help us in understanding these aspects in a better form. So that is the primary aspect of the moon, which we all, need to understand. Apart from that, there are several other aspects, and there are newer aspects that are coming, like in situ resource utilization, habitat, exploration of the moon, exploration from the moon, astronomy of the moon. All these are there. But the basic scientific inquisitive is to understand ourselves, our presence, and evolution of terrestrial planets and solar systems. I will not dwell upon much on this aspect because this is a different topic. But of various aspects, one of the important aspects which needs to be understood and which needs to be understood in detail under different perspective is the temperatures. So before going to actually understanding the temperatures of the moon, so first let us have a quick comparison. So this is our Earth and see how big is our Earth. So if you go to numbers, it looks something like this. So moon is Earth's companion. Moon revolves around Earth. Earth-Moon system goes around the sun. So if you look at Earth-Moon combinedly is called as a system. But it doesn't mean that both are same. Both are quite different. So if you look at the sizes, the tilt, I will come to these details till later, then the temperatures and so on. One of the important aspects is Earth has relatively thick atmosphere. Moon doesn't have any atmosphere. Why I'm particularly talking about is it is one of the important aspects that will drive the temperatures and thermophysics. And why you may be having a question, of course, this is not the forum to discuss that aspect, but why Moon doesn't have an atmosphere? In simple, I understand that there are different range of audience, including students. To put it simple, I would say that Moon is relatively a very small body. You can say 3,500 kilometers in diameter compared to around 13,000 kilometers of Earth. So what? So if you go back to some of your high school classes and undergraduate subjects, you might have heard that our solar system, each planet has formed from a melt which cools down. So cooling means it should lose its heat and get solidified. Because Moon is a relatively small body, it cools very fast in the first few hundreds of million years. So it didn't give any much time to evolve further. So Moon has formed in the very beginning and stayed like that, whereas all the planets started evolving because of the intermediate. So take it from me. So I'll not go into the details. So that's why Moon doesn't have an atmosphere. Other terrestrial planets do have atmospheres, which are still evolving. Another important aspect, what fascinates is Earth has lots of water at the surface, which is in liquid form. But Moon doesn't have liquid water. There are evidences that Moon has ice at the polar regions. Why and how? I'll come to that. Apart from that, if you look at the key distinctions, Moon doesn't have any active atmosphere, so there is no erosion, either wind or water. Earth has atmosphere. Moon and Earth both will get the same amount of impacts. But Earth has an atmosphere which protects itself from the impacts, whereas Moon doesn't have any atmosphere, they impact directly. And there is no geological activity like volcanism and tectonism in Moon. Since there is no geological activity and Moon is almost considered as dead, so there are no moonquakes. Of course, some small moonquakes are observed, which is still under investigation. And there are no active magnetic field. Yes, as I have already told you, Moon is full of craters because there is nobody to protect it. Earth, although it should have full of craters, there is our thick atmosphere protects from having those impacts. So if you put all these things, we can simply say that Earth is active, geologically active, Moon is geologically inactive. So if you put this in perspective, what can we say? Earth is benign, Moon is harsh. Why it is so different? Because although they have shared the same initial epoch of the solar system, because of that size and also because of other characteristic properties, they evolved completely in a different way. That makes Moon special, although it is a part of Earth-Moon system. At the same time, although the Moon is harsh to look at, but it is scientifically interesting and prospecting because Moon preserves 4.5 billion years history of our solar system, which no other object in the terrestrial planets or solar system preserves. So if you can understand and study the Moon, you can better know about our solar system as a whole. Is it the only thing? No, that is only scientific inquisitive. There are several other aspects. Water, habitability, future lunar exploration, further space exploration, and so on. But if we want to do any of this, first of all, we should know how to be there. We are our made instruments. So we should know what kind of environments prepare. Then we should know how can we tame such environments. So since the topic is temperatures and thermophysics, so I will go to a simple cartoon. As you can see, sun is the source of energy for all the planetary bodies, both for Earth as well as the moon. And sun is always shining, giving radiation in the entire electromagnetic spectrum, particularly in the visible and IR, which provides ample amount of heat. But you can see the same sun is shining on Earth, is shining on the moon. But the Earth is happy. That means it is benign. We are staying here. But the moon looks very sad. Why is it? Because Earth, apart from other aspects, Earth doesn't experience extreme temperatures. Whatever temperatures Earth experience are more or less comfortable, in the sense that we are staying here for human life, for different kinds of life forms. On the other hand, moon experiences an extreme range of temperatures, which we cannot even imagine. So what are the kind of temperature extremes on the moon? On one side, day side particularly, moon sweats. Means, I'm just putting it as an analogy. Sweats means it soars in lot of heat. What does it mean? If we look at moon rotates and revolves almost in the same period, which is 29.5 Earth days. It means one rotation period is 29.5 Earth days for the moon, which means half of it would be the day, half of it would be night. So 14 days you will have the day on the moon, 14 days you have night on the moon. When there is day, the sun shines on the moon, heating it to temperatures of around 400 Kelvin. 400 Kelvin, if you convert, so it comes to around 100, 125 degrees Celsius. When night sets in, the temperature goes down to as low as minus 200 Kelvin or beyond. Sorry, what do you say? 70 Kelvin or so. It means it's extremely, what do you say? It is extremely cold. There are reports where it was shown that it can go around 50 Kelvin. 50 Kelvin means minus 220 degrees centigrade. So during daytime, it is extremely hot. During nighttime, it is extremely cold. This is one aspect. These are the kind of temperatures. That means it is continuously distilling. And is it the same all over the moon? It is not same. There is a whole set of diversity of these temperatures on the moon. So I have shown that during daytime, it would be sweating, it would be boiling like anything. During nighttime, it would be freezing like ultra cold freezing. So why is it so? So before going or entering into this understanding of why moon experience such and what are those implications, let us go back to some basics of temperatures and thermophysics so that we can understand better. So basically, these are some high school definitions which you might have all read. So there are three things: heat, temperature, and radiation. Basically, we call kinetic heat, where the kinetic heat is nothing but the energy of the particles which are randomly moving. in a medium. So how do you measure this kinetic heat? It is measured using a parameter called as temperature. It's a kinetic temperature. So the amount of heat which is concentrated within a given volume, you can call it as a temperature. Temperature is measured using a thermometer. Now, if you have temperature, what happens? Conservation of energy. It should utilize its temperature to something. Otherwise, it will have to exchange its temperatures to somewhere. So, if there is a heat, we know that there are three modes of heat transfer: conduction, convection, and radiation. If you take two bodies having some amount of temperature difference, putting together, they will transfer heat through conduction. If there is an atmosphere, they will transfer through convection. If there is no atmosphere, the only way of transfer of heat is radiation. And if you go to more technical details, it is usually defined by your Stephen Boltzmann. But an ideal black body should absorb and should radiate. But nothing is ideal. So what happens is there is a thermal property called as emissivity. Emissivity is the ability of a body to radiate its internal heat, and that is dependent on temperature. I will come to these details little later. So if we have some system or a body or a surface of a planetary body like the moon, Mars, Venus, whatever it is. So the basic energy source is sun. Sun gives some energy in watts, which reaches the surface, and this energy will impart the kinetic heat, which is evident as temperatures. If you put everything, you can put it using our simple Stephen Boltzmann equation, where P are in terms we call it as a Q, which is the total radiated power from the source. Then you have T. If you put it, it is P directly proportional to fourth root of T, T to the power of 4, fourth power of T. So in this case, you say E is emissivity, which I have defined. Sigma is Stephen Boltzmann constant, and A is the area. So if you consider all these are constants, for a constant surface, when sun is shining, you put Q, you put T power 4 here. So usually the sun, what's this? We call it as a solar insolation or sun radiation is around 1300 watts per meter square, which will reach everywhere. Of course, depending upon the distance of the sun. If you took Earth and Moon will receive 1360 watt per meter square equally. But what happens is Earth has an atmosphere. So beyond the atmosphere, the top of the atmosphere, Earth receives 1360 watt per meter square. Moon doesn't have an atmosphere, that completely it comes down, which will heat the surface. And this is the relationship. So if you rewrite in terms of T, then you will get a fourth root relationship, and you can try it at your homes. Like if you put this power reaching, what would be this? So if you have 1300 watt per meter square, you can have T coming to around 400 Kelvin for conditions of the moon. If you have around 700 watt per meter square, you will get, of course, these are variable, but if you consider constant emissivity of 0.95, 0.96 kind of thing, which is applicable for moon, so you will get around, what do you say, around like a 320, 350 kind of thing. So as the influx, this we call a solar influx decreases, temperature decreases. In other words, the surface temperature or the temperature of a body is directly proportional to the solar influx. Okay, so this is a simple relationship where you can simply calculate, given incident power, what would be the temperature. So this is known. So this is the basic thing which applies to even planetary surfaces for Earth, for Moon as well. But as I have already told you, our Earth is very happy because it has an atmosphere. So sun gives radiation, particularly the heating radiation in 1360 watt per meter square. But the entire radiation is not reached at the surface because it has several other sinks, like your atmospheric structure is there. Then you have clouds, you have aerosols. There are several things which are, in simple sense, I said that we eat up all the radiation, only a fraction of the radiation comes to it. How does it happen? It happens something like this. Look at the left picture. 100% total solar radiation means around 1400 watts per meter square, which will reach the top of the atmosphere. But Earth has clouds, atmosphere, etc. So 30% of them are reflected back. Just they don't allow to just come in. Around 20% are absorbed by the clouds. So 50% is straight away gone. 50% comes, but because of the density, so everything will not get absorbed by the species. They directly come and heat up the surface. At the same time, we have another phenomena called as greenhouse effects, which I don't go into details. So if you put it into the numbers, so actual actual radiation what we receive on the Earth is not 1300 or 1400 watts per meter square, but it is around 300 to 400 watts per meter square, which is actually experienced by the surface of the Earth. Of course, we have hydrosphere, we have our planetary boundary layer, we have other phenomena, and all this working in tandem keeps us very comfortable to have benign temperatures and persistence of life on the Earth. So Earth is very happy, as I have told you. But if you go back to the moon, moon is very unhappy. Of course, here I have not shown sun. Sun is somewhere here. 1360 watt per meter square is shining. Apart from that, there are several other things. What are they? Solar wind contains high energy protons will come and hit the lunar surface because there is nobody to shield. There are solar flares. There is galactic cosmic rays. And apart from that, there are meteorites. Meteorites and micrometeorites do hit the Earth, but they cannot enter. As soon as they come into the Earth's atmosphere, they get ablated. So only a very, very, very small fraction comes. Whereas moon is not like that. So meteorites and micrometeorites continuously bombard and they make the life of the moon a very difficult place. Apart from that, moon might be still happy if it would have to sustain this for some smaller length of time. Maybe 24 hours, okay, fine, chalega. But it's not like that. It has to sustain it for completely 14.5 Earth days because day is very long. So moon is not at all happy because all these guys are hitting. And it has to face the solar radiation for almost 14.5 Earth days. It doesn't have atmosphere to protect. It doesn't have liquid water. It doesn't have enough gravity. So there are several things which makes the moon a harsh place to deal with. As we are discussing about the temperatures, we will not go to the other aspects. But we would like to see, okay, fine, all we are not bothered about. But what about temperatures? So as I have mentioned in one of my earlier slides, it will experience extreme temperatures. And what are the key reasons for experiencing extreme temperatures? There are 3 key reasons. Before that, I'll show you one of this picture where this is taken by a NASA LRO diviner instrument. And if you see, this is mostly, this is for a polar region. You see 300 Kelvin and this is 25 Kelvin. You can imagine the temperatures in centigrade. It is hardly 25 degrees centigrade and it is minus 250 degrees centigrade. And within that, you see the variations, you see all colors, particularly in polar region. I'll show you some more pictures in later slides, where you will see this 300 going to 400, that means 100 degrees. That means ultra frigid zone to this. Since this is a polar region, we don't expect 400 Kelvin or so. But what I wanted to say is, it is not uniform. In one point you see, here you see a red, that means it is okay, fine. The very next point, you see it is extremely cold. This is how it is on moon. It is very difficult. And what makes it to have such extreme temperatures? There are three aspects. The first one is no atmosphere. Moon doesn't have any atmosphere. Moon has a very low axial tilt. I will explain you what is low axial tilt. Then space weather. So having no atmosphere, I have told you, explained you in my previous slides. I'll not go into details, but what I want to tell you is, since there is no atmosphere, there is nothing to absorb. The entire solar radiation will come to the surface and propagate to the subsurface. A part of which will be radiated to the space, which is again not effective because there is nothing to take it up. Radiation is compared to conduction and convection, radiation is a very poor or lethargic mode of heat transfer. So it goes in, part comes it, but it doesn't heat up the whole moon because there are some other problems which I will discuss. So it will go to some top superficial layer. Some part of it will try to go inside, some part will try to escape. So you will have a large gradient in the topmost surface. Now, this is very interesting. We all have seasons. Particularly Earth has seasons. Mars has seasons. Because these are the tilt of all planets. So all planets have some tilt except for the Mercury. So Mercury also doesn't have seasons. We have 23.5 degrees. So with respect to equator, sun moves 23.5 degrees this side, 23.5 degrees this side. So at least for 6 months, the poles, one of the poles can see the sun. But it is not case with respect to the moon. If you look at the Earth, moon, and sun geometry, sun is somewhere here. Moon has 23.5 degrees of axis. What is it? Tilt. Moon has only 1.5 degree of, it's almost negligible compared to its size. So if we look at what happens is, with respect to equator, sun moves only 1.5 degree and 1.5. So if you subtend it, direct sun is never seen by these high latitudes. Poles will never see sun. So because of this, there would be some places at poles which you can see, they never see sun, particularly the craters. Elevated portions can see sun because they are at a height, but the craters, the dips, will never see the sun. And they have never seen the sun for billions of years, which is one of the aspects to say that it can harbor water, which is an important. I'll show you one animation made by Alaro. In polar regions, there are two types of places. One place you will never see sun, and one place it will never become dark. So some places which never become dark are called as the places of eternal light. That means they never become dark. So you may be wondering why I am telling all this, because a body or a surface with no atmosphere and no radiation. If it has radiation, it will have a higher temperature. If it doesn't have a radiation, it will have extremely low temperatures. And if it has a radiation and it is at an angle, because sun cannot see directly onto the lunar surface, as if you go back to the Stephen Boltzmann equation and you calculate the temperature, see, instead of, if you take the cosine of the angle of 1360 cos of 80, you will get a flux of around 200, 300 watts per meter square from 70 degree onwards. 200, 300 watts per meter square will give you a peak temperature of around 300 Kelvin or 270 Kelvin, which means even nothing is done, the temperatures are very comfortable. So, a crater here is very harsh, extremely cold, but a peak here is very nice. It is not hot, it is not cold, but it's perfect. So why this is important? It is important in view of the future habitats, in view of future experiments which have to work for a longer length of time. So understanding temperatures and their variability at different places on the moon is also important for future activity. I have told you it is important for science. It is important for resource prospecting to understand ice and all. Now it is also important for any future activity, habitat, or staying on the moon. So this is how what I was talking about. You can see, I don't know, there is some problem in, okay, let me go back and again play. You can see this darker are always darker. This illuminated are always illuminated. If you look at this is the darker portion which will never get light, and this is the illuminated portion which is always illuminated. So this is the kind of drastic change which matters a lot for future exploration. Now, no atmosphere. That is why we have extreme temperatures which have both local, regional, and latitudinal variation. Then axial tilt. Because of the axial tilt, moon poles and high latitudes will never see sun. High latitudes will see grazing sun, and the poles will never see sun. And having it is also an advantage because you can have places of eternal light with no shadows. So you can establish lunar bases in such places. But this is only with respect to the solar radiation. What is incident, how much it will heat up. But there is another problem, another culprit, what is called as space weathering. When there is no atmosphere to stop, particularly the solar wind, cosmic ray, micrometeorites, everything comes and continuously bombards the lunar surface like this. They exchange energy. They interact with the lunar minerals. I'll not go to the details, which is ultimately the reason for production of hydroxyl and thereby water molecule, which we see and discovered by Chandrayaan-1 and being followed up by other missions. Then micrometeorites. These are one of the major culprits. They continuously bombard smaller meteorites. Then when they bombard, they deposit a lot of energy. Not only that, whatever solid surface is there, it gets fabricated into small grains. But that is not end of it. It is continuously being bombarded. Again, next one is coming. Next one is coming. So what happens is, this, let us consider a rock of around 10 centimeters. It is being continuously bombarded for several years. So it will be no longer a rock. It will become some kind of grains. If you continuously bombard it, it will become very fine powder. That is what happens. And this fine powder will not stay. Once a meteorite hits, it will churn and take this material here and put it here. So not only it will modify the surface, density of the surface, porosity of the surface, but it will also churn. Churning means it will mix up the upper layers. So ultimately what happens is, rather being a solid layer, there would be a gradient of density. and gradient of porosity. More the finer finer the particle is, more is the porosity. More is the porosity, more is the voids. Voids, by voids I mean there are two particles and there is a gap between them. These are the voids. And why I'm talking about voids when I'm talking about temperature? Because if you have a solid body, heat can transfer through conduction. If you have particles arranged and with voids in between, the contact points are only this. So conduction can happen only at the contact points, like this. But this is radiation which is poor. So heat cannot transfer very fast in a material of higher porosity. Simple example. You take a metal blanket, however thin it is, you take a woolen blanket. Simple example is that it has this conduction and that is a porous media. So it has a low density. So it will not allow heat to transfer. So this is a simple analogy. So what happens is this will make a layer on the moon which acts as a thermal blanket. What do I mean by thermal blanket? It means that it will neither allow heat to go in. If some heat goes into it, it will not allow it to come out. And interestingly, this all story is happening for last 4.5 billion years. So this layer will go on increasing. So usually this is termed in lunar, called as lunar regolith. But still there is a debate of how much thickness of this layer is. I'll come to these details a little later. So a lunar regolith is formed everywhere, means in simple sense, you say it's a dust. You don't see a bedrock. So you see dust everywhere on the moon, and this dust is also responsible for having extreme temperatures. Why and how? I'll come in the subsequent slides. Now, I have given you the story of why moon has extreme temperatures, why temperatures are important, then what are the factors which will make extreme temperatures. So these are all like some kind of understanding based on whatever whatever literature is there, whatever physics is there, whatever calculations we do. But how do we ascertain that it is correct? So of course there were some measurements. And these measurements are from variety of forms. And this problem of understanding the lunar temperature is not today's, not with Chandrayaan 1 or Chandrayaan 2 or LRO or Apollo. So it started way back in 19th century, around 1868, where people were gazing at the moon using small telescopes. And particularly one set of measurements, which I do not know whether you are aware of, these are called as eclipse measurements. If you want to understand about a surface, what you should do is you put it under eclipse. That means you illuminate, make a shadow, and illuminate. So, why means you are changing the influx very fast. So, from illumination to shadow means from day to night. Of course, it's a long thing. Eclipse is a small time. So, from day to night when you go, from night to day when you go, the system responds. Like, for example, if you have a metal, it responds in a different way. If you have a blanket, it will respond in a different way. For the same amount of heat which is influx, that will tell about the properties. So one simplest physics is that the response of the system, if you look under eclipse, you can tell about the thermophysical property. And if you tell about the thermophysical property, you can tell about the nature of the material. This is the basic physics which has gone into it. People observe through telescopes, okay? And from that, basically IR, infrared telescopes, then they could see some variations. And they estimated some temperatures of the moon. Then they are followed by in situ observations by lunar landers, which are unmanned missions like Surveyor series. Then there were actually, during Apollo times, there were a suite of experiments, out of which one important experiment is the heat flow experiment. I'll not dwell upon heat flow in this lecture because that's a different topic. But why heat flow is there? That heat flow will tell you about understanding the interior of the moon. If you know the interior of the moon and heat flow, you can reconstruct the evolutionary history of the moon. That is the scientific requirement. And to do heat flow studies, you need to go to deep. So how they did, I will explain in brief. But they had really measured lunar temperatures in situ using manned missions. And after that, there were no measurements. And after LRO, during 2009 and beyond, there is one instrument on board LRO called Diviner, which has mapped the global surface temperatures and gave us a lot of insight into the thermophysics and temperatures of the moon. That is now you can call as a basic source for all our understanding. Then it is followed by Chang'e microwave radiometer. Of course, it will not give the surface, but it will give down to subsurface, which is also important to understand. Then followed by our Chandrayaan-2 DF-SAR, dual frequency SAR, which is doing observations. Now, are these observations just sufficient? Or do we need anything more? No, these are not just sufficient. Because they will give you a one-time observation or a one-place observation, or they will tell you about only a limited scales. If you want a better understanding, then you have to calculate the things based on these observations. So you need thermal models. Of course, there were a range of thermal models that have been developed. And in recent times, there were a different kind of thermal models to better understand the moon. Of course, we have also developed a three-dimensional thermophysical model for the first time to understand the moon in a better. I'll try put up some light on these aspects. So if you start with ground-based observation, I have told you this is an eclipse observation. The first ever such kind of observation was carried out in 1868. If you see, things start from 1868 down to 2023. Of course, now there are not many ground-based observations, but late 80s, people have used it. So based on this eclipse measurement, they have first proposed that moon is not rocky. It may contain a dust. And how can you say about the dust? By looking at the thermal response. What is thermal response? Variation of temperature through time. How it is done? It is simply done like if you look at the temperature variation, it will tell about the thermal conductivity of it. Thermal conductivity of a rock is usually a 2 to 3 orders of magnitude higher than that of a dust. So if you solve a heat equation by looking at the temperature profile as a function of time, you can tell about thermal conductivity. By knowing about the thermal conductivity, you can say what is the kind of material it is, whether it is smaller grains, or it is a dust, or it is a larger grains, or it is a rock. This is the beauty of it. That is how they used to do. Surveyor has given us the first ever in situ measurement. So then you can say that you are saying that Apollo has attempted for heat flow, but why Surveyor has done? Actually, Surveyor has not sent any instruments for temperature measurements. That is not their aim. But as many of you might be knowing that whenever a spacecraft is flown, apart from science instrument, there are several parameters like temperature, currents, voltages. All these things are monitored at different strategic locations to know whether the system is healthy or not. What is the conditions it is encountering. So those are called as housekeeping practices. So for surveyor, what they did is they have two electronics compartments, as I have shown here. To see whether the electronics is reaching to what temperature, they have mounted temperature sensors over here, which will measure the temperatures. So what happens generally is moon doesn't have atmosphere, as I've mentioned. If this lander is sitting on the moon for a long time, these compartments will come in a radiative equilibrium. Means they come to a temperature equal to the temperature of the surface. So if you go on monitoring the temperature of this as a function of time, it will reach a plateau. Plateau means it has come in a radiative equilibrium with the surface. It is nothing but the surface temperature. So using this concept, they have measured the surface temperature. And by variation of the surface temperature, they could actually tell about the surface material. Usually surface material is mentioned in terms of, defined in terms of a thermal parameter called as thermal inertia, which I'll give a brief about it, which contains the thermal conductivity, specific heat and density. It's a combined product. It's a bulk thermal energy. So they have some idea, like then they estimated from this that moon daytime temperature can go as high as 400 Kelvin, nighttime temperatures can go as low as 100 Kelvin. That is what they saw. Now, Apollo 12 had a measurement, but they didn't have a measurement of temperature on the surface or subsurface. They have a similar kind of thing. They have a thermocouple hanging somewhere, which comes to a radiative equilibrium after some time with the lunar surface temperature. So if you solve a heat conduction equation using this for different material properties, and you solve it in one dimension to the subsurface, you can see. So they have estimated based on this that surface can go to very high as 400 Kelvin, but 10 centimeters below subsurface can be what you say, it can be very stable. You can see this is 10 centimeters. This is surface, a drastic variation. What does it imply? If it is a metal, if it is a rock, 10 centimeters should not make a difference. You see something like this, but it is not the case. So it means the top layer is an insulation layer. So that is confirmed that the top 2 to 10 centimeters or so, at least the top layer is a dust. Although the surface experiences extreme temperatures, it will not allow the heat to go into the subsurface. So this is the first ever subsurface temperature measurement, although it is derived, but it is worth understanding at that point of time. Then came Apollo. There is an interesting story on this. Actually, Apollo 15, 16, 17, all these three carried heat flow probe. Interestingly, they are of 3 different places. And 16 is completely at a diverse location than 15 and 17, which is interesting to see. It is at a highland. And these are at a boundaries of highland and mare. Of course, some other areas, I'll not go to the details. But what happened is, unfortunately, 16th heat flow probe got damaged during operation. So it didn't give any measurement. We have this 15 and 17, but they are in some area of suspense. Means we cannot clearly say what it is. So although we have some idea, but still no such experiments have been flown. So, but they have given us a quite good information about the temperatures and heat flow. Now, as you are aware, the Chandrayaan-3 is now orbiting the moon and it's going to land at a high latitude site around 69 degrees. So, and one of the instruments aims to understand the surface and subsurface temperatures and their flow, heat flow. And this is very unique. And for the first time we are doing. Why I have made this statement? When Apollo has done, I will tell you in a little. But we are going to measure surface and near subsurface temperatures using the experiment on board Chandrayaan-3. Now, let us have a look a little bit about how Apollo have done and what they have done and what they got. So Apollo has carried a major instrument because it was a manned mission. They have carried a set of instruments, suite of instruments. One of them is a heat flow experiment. So this is how. This is the astronaut central station, and they have placed everything. You can see one heat flow probe is 4 meters. Means within 10 meters of distance, they have put 2 heat flow probes. Then they have a central electronics. Then the central station. And this is the actual picture. The deployment of various ALSEP suits. So, if you look at this, is just look at this. This is actually a heat flow probe. And look carefully on this wire. This is a cable, and this wire has some thermometers, temperature sensors. Okay, so these are called cable thermocouples. And this is not actually a thermometer. This is actually a bore stem into which a heat flow probe is deployed. So why I'm telling you will understand very soon in next few slides. So this is how they have deployed. So how does it look like? This is the heat flow probe where we have thermocouples. You see the length. This is 1 meter. So one thermocouple is here. One thermocouple is here. Means if you start from here, so from surface, one thermocouple is at a distance of 50 centimeters, another thermocouple is at a distance of 50 centimeters. If you look at this, some thermocouple somewhere here, and another thermocouple could be around half a meter away. And what they have is they don't have continuous temperature sensors. If you look at, they have a thermocouple here, they have a thermocouple here, like that. And you see this is 1 meter. And this is almost 10 centimeters. And there are no thermocouples here. Only temperature measurement is done here, 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 here. Actually, they don't want to measure temperatures. They want to measure temperature difference so that they can actually calculate the heat flow Q. What is heat flow Q? It's nothing but minus dT by dz. Variation of temperature as a depth. So this is how the astronauts have literally drilled. They have drilled. They have emplaced bore stems, and they have conducted the experiments. So there is one video. So this is how they have drilled. Because it was a manned mission, there was a privilege to actually drill it. You can see another astronaut is deploying. He is drilling a hole for to deploy the heat flow probes. So on every side they did like this. But Moon is an unknown territory. What happened is, although they tried to deploy the thermocouples down to 2.5 meters depth, they could not do so because of the uncertainty of subsurface regolith. Somewhere they encountered rocks, somewhere they encountered smooth surface, somewhere they encountered very hard surface. So what happened is, although they wanted to deploy it down to 2.5 meters, they could not do it. So some of them have just left on the surface. Some means Apollo 15 was a difficulty, that place, but Apollo 17 they could do it. And from that, they have derived. So I'm specifically telling derived. Derived means they have not measured actually because they don't have temperature sensors to measure. But they have thermocouple here, and using the same radiative equilibrium principle and whatever I have explained, they have measured and derived the surface temperatures. We agreed with the Apollo 12 data. Why the range of temperatures during daytime are agreeable, nighttime there is a discrepancy. And why nighttime discrepancy? I will tell. But during daytime, when you have 1400 watts per meter square, any small variation is not, because that is the forcing which will give maximum temperatures. And during night time, when there is no excuse me. During night time, when there is no solar insolation, it becomes just a function of thermophysical property. So from that, you see, Apollo 15 could not be deployed proper. Apollo 17, they could deploy down. But anywhere you see, it is beyond 50 centimeters. And particularly you look at this region, top 10 centimeters, there are no direct measurements. That is why I always say that we are, from Chandrayaan 3, we are doing for the first time, first ever in situ measurement of the top 10 centimeters. And why top 10 centimeters is important, you will appreciate now by this time, because the top 10 centimeters is a fluffy layer, a dusty layer, which will have extremely low thermal conductivity, and which is necessary to understand if you want to understand how heat propagates from the surface to the subsurface. So there are no direct measurements from the crucial superficial layer. I will not dwell upon. So what just wanted to tell you is that these are the diurnal variations during day and night, daytime temperature, maximum, minimum. But once you go down to 50 centimeters or beyond, there is any significant variation. And one more thing, it is not just a diurnal variation, not just for one lunar day, but you can see an annual variation. This is 4-year data from Apollo thermocouples. You see these oscillations. And these oscillations are correspond to annual variations, because the Earth, Moon is rotating around the Earth, revolving in itself. The Earth-Moon system undergoes revolution around the Sun. So it is equally important to have those variations. So these are annual variations. So that is what we understood from Apollo. But beyond 2008, Chandrayaan 1 followed by LRO in 2009, they operated LRO. There is one instrument called as a Diviner Lunar Radiometer, Diviner DLRE, Diviner Lunar Radiometer X. So this is the instrument. I will not go to the details, but this is what it is found. If you calculate, as I have told you, from pole where there is no flux, 0, there is 1400 watts per meter square flux. As a function of, if you take the cosine of the angle, this is the kind of flux what you see. What I have told you is that around 300, 400 is a good flux where you have a comfortable temperature. And Diviner has mapped the latitudinal variation of temperatures, as you can see here. This is a model, but this is this. And if you look at the equator, it can go as high as 350 Kelvin during daytime, and it can go as low as 100 Kelvin during nighttime. But if you come to poles, even daytime, you will have only 150 Kelvin. During nighttime, it can go as low as 50 Kelvin or 70 Kelvin. So this is the first time we got the complete global surface temperature variations from Diviner. Then we are talking about surface. What about subsurface? Subsurface also have the same thing. If you see equilibrium temperature at the surface, it is 250 Kelvin, which is also measured and established from Apollo. But if you look at pole regions or high latitudes, it is not 250 Kelvin. It would be slightly lesser. Around 200 Kelvin is the subsurface temperature. Maybe it is 100. But these are only modeling studies. We don't have measurements. And they may change. Why they may change? They may change if the topmost surface is different. If a heat for 4.5 billion years, some heat has entered in it and it cannot escape, you may see a surprise where you can see larger temperatures as well. That needs to be understood. Now, Diviner has given very beautiful pictures of the daytime and nighttime temperatures, which have a lot of applications to understand the water ice, to understand the pockets of water ice, to understand the mineralogy, to understand the dust, to understand the, rocks, all those things. And these are the 2 global maps from Diviner. And this is the diurnal variation. This is how you can see, you hardly see any gradual variation during day and night time. This is dawn and dusk, you see significant variations. But your polar regions, you see a lot of colors here. So equators are important in one sense, but thermophysically high latitudes and polar regions are more complex and more important, and it is necessary to understand because we don't have much missions or much understanding. There are several other observations from Diviner where they have found thermophysical properties. I will explain what it is. You see, this is all green. See, it is the same scale. I have not put the scale here, but it is the same scale. Your red means you can consider as a high, very high 400 Kelvin kind of thing. Your blue is your, your 100 or 50 Kelvin kind of thing. If you look at that analogy, you see among the greens, you have one red spot. Okay. So what they have found several things. It is morphologically and thermophysically distinct craters they have found. They have found places with rocks. They have found places with lot of dust. All these things were derived from Diviner. But the basic measurement parameter is temperatures and temperature variation as a function of time, which they have used as an input to a one-dimensional thermophysical model. Now see. This is a famous Tycho crater. Okay, I would have put Tycho actual information. You can have a look. This is actually a famous Tycho crater. It's an impact crater. It is very beautiful looking on the moon. You can Google it. Now, you see, it is very red. Rest all is blue. What does it mean? This is nighttime, map, temperature map. So nighttime, there is no sun. If there is no sun, this is becoming blue. That means 100 Kelvin. It is okay. I agree. It agrees with the Apollo. But it does not agree. What does it mean? It means that it has more heat. What does it mean? It means it has taken more heat and it is releasing more heat. So who will take more heat? Who will have a capability of transferring more heat? That means the material property, thermal conductivity should be. So what are the two types of materials? Rocks and regolith. So rocks have high thermal conductivity. So if you put all this into a story, the bottom line is this area has lot of rocks or debris, whereas this area has lot of dust. And that is true morphologically because this is a impact crater and relatively fresh, young impact crater. So now you will appreciate that temperatures and thermophysics are not just important for understanding water ice or for staying or for saying whether it is comfortable or not. No, they can also be used to understand the surface properties. What are there at the surface? What is the morphology of the surface? So this is another aspect which is important to understand, which will throw a lot of light on our current understanding of the moon and the processes involved. This is the other one which I have already shown. I'll just skip. So this is from the thermophysical part. Now, having looked at all these things, we can now put up in a perspective that moon is not a very straightforward surface of constant thermal conductivity. It can be considered as a layer of low thermal conductivity, a very low insulated layer followed by layers. But it is one layer? No. You can think it of a different regolith structure. So if we put the first few microns is highly powdered, okay, which will come in direct contact with external radiation, means your 1360 watt per meter square is first experienced by that. And based on its property and emissivity characteristics, it emits the majority of radiation. So if it is a rock or having a high conductivity, it will have downward heat flux. it has a low conductivity, it will have an upward heat flux. Then 1 to 2 centimeters, you can have a fluff, very porous layer, extremely low thermal conductivity. So if the surface is young, like Tycho, you will not see any much fluff. But if you have a surface which is as old as 4 billion years, you may see a thick fluff. From Apollo, they have advocated that, means from those measurements, they said that it is 2 centimeters. And till 2010 or so, people were believing it is just 2 centimeters is the fluff, rest is the, what you say, a single layer of higher conductivity. I will come to that, why I have mentioned. Then you can have a...
Durga sir,
yeah.
Sorry for the interruption. Time is running out, sir. Actually, 4:40 we are.
Oh, okay. So maybe I'll take 10 minutes. Is that fine?
No, sir, actually, it's restricted timing, sir. We usually put 15 minutes. That's it.
Okay,
it may
but we have, I think, delayed in starting. That's the reason. Okay, no problem.
It may cut off, sir. It's
Okay.
scheduled timings. That's why.
Right. I'll do one thing. I'll just quickly go. So I'll not go through these details which you have already seen. What I will try to tell is that the thermal conductivity is more important of the uppermost layer for propagating the heat into the subsurface layer, of which the porosity plays a dominant role in dictating the thermophysics. So I'll not go through this because this is thermal inertia, which I have already mentioned. Then thermal inertia is a combined value of conductivity, specific heat, and density. Low thermal inertia is a dust. High thermal inertia is a rock or a bedrock, which I have shown you in the example of Tycho. So this I will just skip. Now newer thinking and newer results show we have posed some questions like why 2 centimeters? What is the role of topography? Because it is vacuum, so and you have heat, it cannot dissipate faster. So all these things have significant impact on the surface and subsurface temperatures. So if you see that if you have a polar site which is 100% illuminated and 37% illuminated. So it all depends upon what is the local topography. Means it is the same site, but if you have a larger topography, the entire area is only 37% illuminated. That means you will get less flux. If you have less topography or plain, it will be 100% illuminated. So less flux will give you lower temperatures, higher flux will give you larger temperatures. So thermophysical properties are, the temperatures are not just a function of the various parameters, but also it's a function of the local surface. Okay, this I have explained you. So now, why temperatures are important? Because they will tell us about the water ice. This is another aspect. And water is a resource which everybody wants to prospect on the moon for future exploration. So these are various examples I'm just giving so that you will get a feel of how abundance maps are made. This is another map which tells about the thermal inertia variation on the moon. And this is one such map for Apollo site. And this is South Polar temperature map, which I have shown you in one of my earlier slides. And this is the Hermite crater, which is the coldest place in the solar system, which is almost like minus 250 degrees centigrade, like 25 Kelvin is the temperature which was detected. So that means you have 400 Kelvin in 25 Kelvin, such a huge variation on the moon. So these are some other pictures of summer and winter temperatures of the moon. And this is some activity which is shown. What would be the delta? If you know this delta, then you can actually calculate whether ice can be there or ice cannot be there in a stable form. And this. So we are going to build habitat. We are going to the moon for resource prospecting. So you should identify sites and see whether these sites are conducive or not. This is one site scouted from Diviner. It's an astrobotic site mission. You can see the temperatures, 80 Kelvin to 140 Kelvin. So they are very benign temperatures. So this such kind of activity is needed, understanding is needed if we plan any future missions to the moon. Now I'll come to our experiment on Chandrayaan 3. It is a chased experiment which is now orbiting the moon. This is the instrument which will be deployed and it will be penetrated and it will provide the temperature profile of top 10 centimeters of the lunar regolith for a high latitude location, which was never made, and it will give you a profile which was not done. So it will give us the first ever understanding of the temperatures and thermophysics of high latitude place of the moon. I'll not go to the details here. Okay, of course, this all has to be supported by modeling. And what does modeling give us? Modeling give us a better perspective. What kind of this? This is one result. This is published recently. You can see this is using modeling. See, using observation, we can get 1 pixel of 300, 400 meters or several kilometers. But if you take this as an input and do a modeling, this is actually the Chandrayaan-3 proposed landing site. And these are the local temperature variation. Just see that you read is and this. So this varies almost like some 40 Kelvin. Means that within a small region of around a few kilometers by few kilometers, you see a significant variation of the temperatures. It is very important, not only for operations, but also to understand how the subsurface reacts. So you can see around 30 Kelvin of variation within the space, means within spatially, or you can see around 175 Kelvin variation during day night. So this is how the localized. This is just 200 meters by 200. You can see blue and red. Blue corresponds to around 100 Kelvin. Red corresponds to around 300 Kelvin. So you see very small areas nearby, few meters, they have a drastic temperature variations, particularly at dawn and dusk, which is important to understand and give nice insights for our future. So if I sum up, I would say that monitoring the temperature, understanding the temperature and thermophysics of the moon is necessary. Here I have so why it is necessary? If you want to understand the evolution of the moon, you need to understand the surface temperature. They will tell about the equilibrium boundary. That will help us in deploying the heat flow probes in future. Is it that what is needed? No. It is also needed, like if we are going to prospect water on the moon, which I have showed you in one of my earlier slides. Then if you want to do in situ exploration and want to stay there for several days, you have to find a location where your temperatures are benign. But you cannot go there and do it, right? So a priori you should do and have an understanding of the places where the temperatures are nominal and you can go. Our temperatures, although they are non-nominal, but you can make it in a way, in a nominal scenario, that will really help out. Then next, we are planning to have habitats on the moon, laboratories on the moon. So understanding the thermal environment of the surface and subsurface is very, very important. And in future, if we want to, like as all nations are thinking ahead, that if you want to have further planetary interspace exploration from the moon as a base, then you need a lot of resources. So if you want to prospect resources, one thing what will help you is the understanding the temperatures, because temperatures dictate the stability and the mobility of volatiles or such resources like water and other volatiles. So in all, understanding and measuring the temperature are, in simple sense, measuring the fever of the moon is at most important criteria for any mission to the moon, past, present, or future. So with this, I conclude. First of all, I'll thank Reactive for giving me this opportunity, particularly to Srinathji for asking me to give this talk, and all the entire Reactive team. And I would like to thank Director PRL for giving me, supporting me for giving this talk, and all my colleagues, students. And it is not my single work, so there are a lot of people behind it. So I cannot name everybody, but thanks to all my supporters and my team and my colleagues and collaborators. So I would be happy to take any questions you have. If you still want to be in touch, there I have my email, which I have displayed in the first, durgaprasad@prl.rest.in. You are free to contact. Thank you very much.
Thank you so much, sir.
Yeah.
Does anybody have any questions? Does anybody have any questions? Or we will end the topic. Okay, sir, I think nobody have any questions. I'll end the meeting. So I hope this message finds you well. On behalf of Creative, I would like to extend my heartfelt gratitude to each and every one of you for joining us today for this enlightened online talk. We also want to express our appreciation to the team that ensured a smooth and seamless experience for all the participants. Once again, thank you for your time, your enthusiasm, and your unwavering commitment to expanding our horizons. We look forward to welcoming you to our future events, sir, and the discussions also. Wishing you all a wonderful evening. Thank you. Let's end the talk here. Thank you so much, sir, and thank you everyone for participating in the talk today.